on how little can two trees agree. So this is a picture from Mike and Laszlo's paper of two unrooted phylogenetic trees. And the trees on the left, this is actually the one on the left is one of Charles's favorite trees. If you ask how much do they have in common, you can see that if I choose 2 and 6, in the middle tree, 2 and 6 are together, and I can only choose 2 more to make a subtree that they agree on. So the largest subtree that they can agree on is actually 4. So this is an interesting measure for how what structure trees have in common. And this is, let's see if I can make this work. There's a whole series of interesting questions based on this idea of what is the agreement subtree and what is the maximum agreement subtree. And from the Isaac Newton Institute problem list, which I think the Isaac Newton semester was, Mike might need to jump in here. I think it was 2006, 2007. Does that sound right? Yeah, okay, yeah. So the question was given, so this is a problem list from the semester at Isaac Newton. And Mike had in his office a crate of wine. And if you solved one of the problems before the end of the semester, you got a bottle of wine. So this was one of the problems. So the question was given 2 unrooted binary phylogenetic trees. And an agreement set for them is a subset Y of the leaves, such that the underlying structure of T restricted to Y and the underlying structure of T prime restricted to Y is the same. And the question was, is there a constant so that any 2 trees have an agreement subtree of at least C log n? And I should say just to start that computing this agreement subtree can be done in order n squared time. This was Mike and Tandy in the Kaikoura tree paper. And Mike and Laszlo showed that the agreement subtree is at least log n. And it was improved by Martin and that to square root of log n. And actually, it's been shown fairly recently that the minimal size of an agreement subtree is theta log n. So interesting results, but there's actually more you can say about maximum agreement subtrees. And so back in 2014, there was a series of talks sponsored by the NSF and the CBMS, so the Conference Board on Mathematical Sciences. They ran a conference on mathematical phylogeny in 2014, and Mike gave 10 absolutely gorgeous seminar talks that became a book. And they had a bunch of satellite workshops. And one of those workshops was I ran, which was supposed to be the whole conference was organized by Joe Rosinko. And there was supposed to be a working group on maximum agreement subtrees for undergraduate researchers. And so the night before this was to start, I was having dinner with Mike, and he said, well, what problem are you working on? And I said, well, I'd like to do something, I'm thinking about doing something with maximum agreement subtrees. And I told him the problem we were thinking about. And, the next morning he said, I think I know the answer. And then for the undergraduate research seminar, we had Mike, who was lovely. And then Seth Sullivan showed up and a bunch of Seth students. And I have to say that we ended up making lots of progress on the problem, but most of the undergraduates ran away. So let me tell you about some of those problems. So it was really fun. And it was a great group of people to work with, but we did lose all our undergrads, right? And so the question we looked at there was inspired by earlier work by Bryant, McKenzie, and Steele that showed the expected mass of 2 trees is square root of n, where n is the number of leaves for a uniform distribution. And they came up with useful recursions for Yule-Tardy. And so this is the work that we did down in South Carolina at Winthrop. And this is with Daniel Bernstein, Lam Ho, Colby Long, Mike, and Seth Sullivan. And so we were able to show that the expected agreement between T1 and T2 is at least n to the 1/8, where n is the number of leaves. And that was for uniform distribution, and we were able to also get bounds for Yule-Hardy. Seth's comment was this was a hard problem not to work on, and so he worked on variations of it. The last time I saw him was actually March 2019, and he was still working on variations of it. And they looked, he as with I don't remember Misra's first name, looked at restricting the trees to the same basic shape, like restricting it to just being caterpillars or other shapes. And they were able to get a lower bound on the expected mass of square root of n. And so there's some interesting questions there. And more recently, as of a week ago, there's a paper by David Aldish that raises the bound to square root of 3 minus 1/2, so about 1/3, with suggestions that this probably should be higher. The Aldish result is for any trees, not restricted to the tree shape, the similar tree shape that Seth needed for his results. So there's some interesting questions here about what can you do and can you make this longer, so, or make this better, tighter bounds. And those are the Aldish is for uniform and does have some bounds for Yule-Hardy. So, okay, fast forward a couple of years, and in 2019 in October, Simona and a group of others organized a seminar at Dogstool, Algorithms and Complexity in Phylogenetics. And as part of that, and I think many people who are in the audience here are actually in this picture for the Dogstool. And so, yeah, so it was organized by Simona, Rolf, Magnus, and Britta Dorn. And we had a working group on maximum agreement subtrees. Also kind of the same thing, but we looked at a slightly different problem at this point. We looked at one of the results from the Martin and That paper was their overall result is the agreement subtree is of size at least square root of log n. And they conjectured if both trees are balanced, it should be at least square root of n. And they also had a lower bound on the balance size of the agreement tree for the balance subtree. So this was n to the 1/7. So while we were in Germany, we worked on this. We were convinced that the conjecture was true and that we probably could improve the, yeah, we were convinced that it was true. I should just say that. And so this work continued. This last meeting I attended, which was at the Sumner Life Saving Club in New Zealand. Thank you, Mike. It was a lovely time. And so we were working on this problem there. And then I should say, we continued to work on it. And in mid-March 2020, most of us were actually in Christchurch, New Zealand. And we heard that the borders were shutting down and we were all going home. And so Magnus was going back to England. I was going back to New York. It was a really scary time, even scarier when we got back, to find, friends and colleagues who had passed away and stuff like that. But Magnus and I were trying to figure out what to do with our last 3 days in New Zealand. So we worked on this problem. And for anyone who's spent any time with Charles, this should be a very familiar site. Is it, Mike, is it still open? Yeah, okay, I was hoping. Okay, so this is the cafe, one of the cafes at the University of Christchurch. And so we were looking at this conjecture. Do you have, if I give you two balanced trees, do they agree on at least square root of n leaves? And it turns out it's false, which was really surprising. And I'll give more details. I just wanted to kind of give the travel log of how we ended up here. And as we were trying to work out the proof, we also sat down and took over the whiteboard in Charles's office and figured out that this is actually this bound with just some very careful reanalysis of the original proof, you can get up to n to the 1/6. We don't think this is the best, but this is what we were able to prove. So, and it just appeared in SciEm Discrete Math, the same issue actually as the Aldish paper. So let me actually give some definitions. I know lots of people know what a tree is, so I just wanted to kind of talk through very quickly and then give you the idea for what we did and what we're trying to do. So we're interested in rooted phylogenetic trees, and we have our leaf set X. Since they're balanced, our leaf sets will always be powers of 2. We're allowing no degree 2 nodes except for the root. And for technical reasons, if our tree only has 1 leaf, we're going to allow that to be both the leaf and the root. And that's just to make some of the math work better. We'll talk about the size of the tree is literally the number of leaves. I'll usually refer to it as n. And we're interested in binary trees. So everyone has 2 children and has at least one edge coming in if it's not the root, and or x equals 1. We'll talk about the height as being the longest path from the root down to the leaves. And again, because it's binary, everyone has the same length path down to a leaf. And we're interested in balanced. So for balanced, we will always have the case that n equals 2 to the m for some m, an integer, and m is the height. So this is an example on 16 leaves, and I'll explain what the blue arrows are in just a sec, but that's our trees. And so what we're interested in is taking these 2 trees and asking what is the largest subtree that they agree on. And so just in terms of this picture, if I have a balanced subtree, and for example, in this tree, I chose 11 and 10, I have to choose 11 and 10 over here. The leaves have to match. And let's say I chose 6 and 7, and I have to choose 6 and 7 in this tree. When we compare the resulting trees, we contract any internal nodes of size 2. So this actually ends up with just the 2 blue trees are a tree on 4 leaves. And this is the smallest agreement subtree between these 2, or the smallest maximum agreement subtree between these 2. So let me explain what that term is, because I'm going to use it over and over again. So we're going to talk about these 2 trees, and we are going to talk about the restriction of the tree T to Y. And so what is the restriction of T to Y? It's, for example, these blue, if I chose the set 6, 7, 10, and 11, the restriction of my left-hand tree to that set Y is the minimal subtree that contains all those leaves and suppressing all the non-root degree 2 vertices. Okay, and I can do that for both trees, both this one here, which I'll call T, and this one here, which I'll call S. If Y is in the overlap between X and X prime, and we do write it this way because we're going to actually start looking at overlaps of subtrees of our initial trees, so they might not necessarily have completely the same leaf set. We'll say that S restricted to Y and T restricted to Y are isomorphic, then we will call Y an agreement subtree. So if among all the agreement subtrees of S and T, the restriction of SY is the maximum size, then we'll call it the maximum agreement subtree, or mass of S and T. And so Y is denoted, the size of Y is denoted by mass to S and T. Okay, so this is just formally the notation that we're going to use for showing things. And so what's interesting is that mass is actually used as a measure of similarity between trees, but it can never take on the value 0. You will always have some subtree that occurs in both. Okay. So here's our results. So the results that we came up with were, if I give 2 balanced rooted binary phylogenetic trees on n leaves, they do not necessarily have a mass of size at least square root of n. So this actually disproves the conjecture of Martin and that. And here's it written formally. For every C, there exists a balanced rooted binary subtrees S and T, where n equals the number of leaves, and the mass is smaller than C times n to the 1/2. And then we were also, as we were going through this, we were able to improve the lower bound on Martin and that on the size of the mass for a pair of balanced rooted phylogenetic trees. Theirs was n to the beta, where beta is approximately 0.149, which is n to the 1. This should be, I can rewrite this as 1 to this n to the 1/7. What were we able to do? We were able to get it a little bit lower and get it, this is about n to the 1/7. We were able to get it to something a little bit better, a little bit bigger than n to the 1/6. Okay, so not great, but improvements. Okay, so let me show you any questions so far. Hopefully all of this is. Okay, let me show you the ideas for how we did this. So the first thing, and this is actually a discussion with the reviewers, was, we actually created the trees. And they're actually in the appendix of the paper. These are the Newick of the 2 trees on 2048 leaves. We needed 2048 to make this work. But this isn't that useful. And that was the discussion about whether we really needed to use 5.5 pages of showing you the Newick to prove that it works. So let's actually talk about how we got it, instead of just saying, here's the Newick and they disagree. Well, the first thing I have to say is the construction turns out to be really delicate, and we needed it to be, n needs to be bigger. This should be 2 to the 11th. N needs to be bigger than 2 to the 11th. Why? Lower than that, it seems we couldn't find a counterexample. So part of the reason we think that Martin and that came up with this conjecture is, for these smaller trees, you can't quite kind of pack enough stuff in there to get something less than n to the 1/2. Okay, so first, it's very delicate. That's unfortunately, but we rely on 2 properties. And so I'm going to say the general properties, and then I'll give a concrete example of why this works. So here's our 2 properties. Each of the balanced pendant subtrees, so each of these little copies of the balanced subtree, can only overlap with a balanced subtree of my other tree in a small number of labels. So what we're trying to do is we're trying to force the agreement subtrees to be small between these 2 trees. And the way we did it, well, first what we did was we scattered. If you think of the first tree as just being ordered, we took the second tree and we kind of scattered a piece of each of whatever level you're going to of the pendant subtrees in it. So we had all of them over here, and we took each one and put them in a different place to force decisions when you're trying to make your mask. So if we spread them out, then if you want to choose something that's way this bottom choice here, and these 2 trees have they show the same structure, but the leaf labels are actually quite different. It's a little hard to see at this resolution. But if I choose, for example, this blue edge here, and I choose this blue edge here, those are now have to be next to each other, and we lose all the rest of the structure. So once you leave a pendant subtree, you end up having to throw away many, many labels that you can't make the structure with, because we need to preserve, if two things are a sibling pair in one tree, they must be the sibling pair in the other tree. So once you do that, you end up being able to, I don't know, pack a lot of things in the other region and be able to do stuff. So first, we're going to arrange it so that two pendant subtrees only have a small overlap. And the other thing we're going to do is we're going to look at caterpillars, which have very small overlap in general. So we'll arrange it so that our trees only have a fixed number of, any two subtrees that only have a fixed number of things in common. And those fixed things tend to be caterpillars. And so add very little to our mast. Okay, so how do we do this? Let me give you an example just for n greater than 2048. These trees are not 2048, these are 128. You can't actually easily visualize the 2048 on your screen. Okay, so here was our idea for kind of in general. We're going to take 2048 and we're going to break into 16 subtrees on leaves 128 on 128. So here they are. There's one on 128. Here's one on 100 and we're going to arrange our labels so that each pair of subtrees only share 8 leaves. So I've taken my huge tree, I split it into 16 subtrees. Each one of those only overlaps with any other choice in my other tree with 8. Well, that's really good because that means that if I chose to match those two subtrees on my mast, they can't add much to the overall score. And each embedded set of 8 leaves in each subtree are going to form a caterpillar in one way and a caterpillar, what I'll call a reverse caterpillar, in the other. And each pair of trees has the shared leaves. Yeah, so as I said, they're going to be a caterpillar going one way and caterpillar going in the other way so that they have almost no overlap. And we end up with a mast of size 32 from this construction. And when we should have had 45 if the conjecture had held. So let me show you what that actually looks like. So what was our goal? We're taking this tree structure and we're trying to figure out where to put all the leaves so that they overlap the least. And so if my tree T is across the top, and these are its various pendant subtrees, and my tree S is going this way, and these are its pendant subtrees, we're going to arrange it so that the leaves that overlap are in sets and are quite small. Okay. And the size of the mast is going to be influenced by these overlaps. So if there are 2 rooted caterpillars, one that goes from 1 to N and the other that goes from N down to 1, they only contribute 2 to the mast. And so we can take those and use them. Okay. On the other hand, if we have balanced trees, their minimal height have less room for these long caterpillars, but we can actually take these balanced trees and split them into these caterpillars, these short caterpillars. Each of those short caterpillars can add at most 2. And when we start summing them up, we end up with much lower than square root of n. Okay. And so when we do this, there's a lot of math behind this, lots of kind of finicky stuff, but we can end up embedding basically 2 to the n minus log n of these n disjoint caterpillars into a balanced tree on 2 to the n minus 1 leaves. So we can take these blue guys and the green guys and embed them in a very, very convenient way so that they have little overlap. Okay. And Oh, I had one more slide. So let me go back to this one. Sorry. And so, no, I'm not finding my slide. Okay. So once we do that, we sum things up and things work out really, really well. And we end up with this lower bound. Okay. Okay. Any questions so far? Everyone's good? Not seeing any questions. Okay. So then our next question was, what do we do next? Like, how can we make this better? We were really surprised that this worked. And we were interested in the Martin and that had a lower bound of basically end of the beta, where beta was 0.149. We've just shown that the square root of n didn't work. So can we make this beta bigger? And so this is a picture of Charles's office, and us trying to figure this out. And so how do we do this? Well, we actually sat down and went back to the Martin and That's original proof and just very, very carefully improved the bookkeeping. So to do this, we actually relied on it. The original proof relies on the recursion of Steele and Warnow for computing the mast. And the way that they think about it is, if I have two phylogenetic trees, S and T, I can look at their left and their right sides. And we can think about how to compute the mast. Well, the mast can be done recursively. Thinking about it this way, if I take the mast, one thing I could do is I could align up the left-hand sides of my original tree and the right-hand side. So I'm going to end up with however well the mast lines on the left, however well it lines on the right. I could flip those. That's this next line, is flipping these so that they go the other way. And then we can also do things like completely throw out the left-hand side. Like, just think of aligning all of tree S with the left-hand side of the tree T, and all of tree S with the left-hand side of tree R. We can do one or the other. We can't do both to keep the structure. And similarly, we can do all of tree T with part of the S subtree left or right. So these are the choices that you have, and you literally can compute the mass this way. Just keep recursing downwards, and it doesn't, and you're taking the max of the result. So when you're actually working out the recursion for these bounds, you have to think about what happens for each one of these and work through equation after equation after equation. And once you do, you end up, after lots and lots of bookkeeping, you end up with the original bound of 1/7 could be improved very slightly to, or so 1/7 could go to 1/6. That was our improved bounds. Oops, sorry, because we're not meant to disappear. Okay, so I wanted to talk more about open problems than I did about what we did, because there's, I don't know, it's cute, but I don't know where to go with it. And so one of the questions are the bounds are tight for the general case due to Markin, but the question about the asymptotics still remains open. The questions that Mike and Seth and all of those folks were working on. So how can we improve the asymptotics to be stronger, to be larger? And then the other question, which our proof method does not extend to, but how can you come up with better lower bounds for balanced trees? So we have n to the 1/6, but no one knows any examples of mass for balanced trees that are smaller than n to the quarter. I should say this should be n to the third. So it does seem like these should actually be, these should be much higher for our overall bounds. So, and I'm gonna Yeah, sorry, this is gonna be super quick today. I wanted to thank what made all of this work possible was Mike and the Erskine program and all our hosts at the University of Canterbury, as well as Slosh Dogstuhl, the Leibniz Center for Informatics in Germany, the Simons Foundation for Collaboration and Travel, the NSF for their generous support, and Sean for actually being super helpful through this whole process to all the collaborators on this project. And that's it. And I'm happy to take questions.